Okay, good morning, everybody. Thank you for coming to the presentation. My name is Jay Nagle. I'm a product line manager at onsemi, focusing on the industrial market segment. Okay, so we're going to talk today about power semiconductors for Industry 4.0. And then just before we jump into the topic, want to give a little insight into what our strategy is, what our corporate strategy is, and having an understanding of that. Right now, the automotive and industrial markets are accelerating. So the acceleration is happening mainly in automotive for electrification and ADAS. In industrial, a big part of the growth is this Industry 4.0 initiative, with that big goal of increasing efficiency in the manufacturing and plant processes. So the acceleration of this market is going to require an increase in electronic content and power delivery due to an increase in computing requirements and system architectures to be able to create that sustainable footprint. So our corporate strategy is really predicated on creating that synergy between intelligent power and intelligent sensing for both of these markets. That's what we're going to need to be able to create the semiconductor that's going to be needed for both Industry 4.0 and for the automotive market. And so what is the meaning of this synergy? Like, very, very simply, for high power efficiency and energy conversion, it's absolutely necessary to be able to sense real time what the power system is trying to deliver to the load and then execute on that efficiency. To be able to do that, we've taken a market leadership position in power discretes. We're one of the top 5 in the market today. What comprises that is silicon carbide and silicon discretes and modules that contribute to intelligent power and sensing for charging stations and energy infrastructure, and then also factory automation. Okay, so we do that through the creation of cost competitive, lower weight, high efficiency, and diagnostics at the system level. Diagnostics is very important for the intelligent power and the intelligent sensing aspect of things. So efficiency in the industrial market just doesn't translate into automotive, right? So Industry 4.0 and now this emergence of Industry 5.0 focuses on humans and machines working side by side to automate and create the factory to increase output efficiency for all plant processes, all the way from the beginning supply chain, throughput increase, and increasing of the accuracy. So some of the mega trends that are driving Industry 4.0 right now, it's digitization of vertical and horizontal design change, Internet of Things, having effective connectivity from start to finish through applications such as asset tracking. And then automation, it's really a coordinated synchronization of robots, forklifts, guided vehicles, and humans all working together. So safety becomes paramount of importance. Logistics, optimizing the supply chain and delivery using mobile delivery vehicles and drones that are electrified and battery operated to reduce those greenhouse emissions. And then innovation. It's innovation in how you run the plant, and it's innovation in product and system design. So the key applications, collaborative robots, mobile robots, delivery robots, drones, forklifts, and then asset tracking. These are some of the key applications that's going to support Industry 4.0 and 5.0. So what is needed from the semiconductor industry for 4.0? So you need high power efficiencies to extend the battery life. You need cost and weight reduction because you're going to have a higher volume of electronics in both the vehicle and the plant. With the integration of this extra power that's needed, integrated safety and diagnostics, the ability to detect any type of faults and then react to those faults. And then high reliability and lifetime. These plant processes, they're going to require operation at really long time intervals to be able to increase the throughput. So the more that you can extend the battery life, the more you can minimize the downtime, the more reliability you have in the semiconductor, the more efficient your process is going to be. So some of the primary systems in an autonomous mobile robot, and I'll give you that as an example. You've got the traction and servo drive, and you also got the multi-axis motor control, right? So what that's going to comprise is going to comprise silicon MOSFETs, power switches, silicon carbide. I'm going to get into that a little bit later on. A lot of you might be wondering, oh, silicon carbide, it's really only for automotive and solar systems, but there is some applicability to plant processes as well. You also have the gate drivers, controllers, power modules, integrated power modules. So the more integration that you can have, the more that you're going to save on the cost, the more that you're going to be able to have a more compact space. So for higher power levels, integrated power modules with integrated functions and diagnostics is going to be the key. PFC and LLC controllers. These are important for the battery charging. And then any type of power that you provide from the grid to have an efficient power source. And also going into the power and signal management. It's very important in the power management to have high efficiency, especially with synchronous rectification, also with DC to DC converter applications. And then for that feedback loop that you need in the intelligent sensing portion, op-amps for signal measurement, right? Op-amps are going to be very important. And then also the LDO, the low dropout regulator. It's a very small device, but it provides a very low noise power rail with a low quiescent current. That's going to be key to saving the battery life. So a lot of semiconductor companies right now are coming out with that technology that's going to feature that low quiescent current. And then connectivity with Bluetooth and visible light communications. And then for object detection and orientation, LiDAR and imaging. That completes the whole loop. That completes pretty much the whole system footprint from an electronic standpoint. And then a little bit of shameless promotion. You have onsemi all over the footprint. So we break the system down further into the system architecture to show, the complication that goes into it. So just pointing to specific areas of the system, you've got the AC to DC conversion for any three-phase or single-phase input. So silicon carbide and silicon carbide discretes and module they're power semiconductors that enable hard and soft switching in PFC and LLC resonant converter applications with controllers that are needed to implement certain modes like continuous current mode that you would need in a PFC type of configuration. You also have battery operated. So most of this is going to be battery operated. You're going to need the battery and the charger. So some of the essential components that you're going to need is what we see there as the SOA FET, so the Safe Operating Area MOSFET. You need a MOSFET that has, or a power switch that has a very wide safe operating area so you can handle any transients from the battery. And then small signal components. So when we talk about small signal components, it's BJTs, diodes, things like that are going to be needed for cell balancing, okay, for all the different cells in the battery circuit. This is going to really contribute to the efficiency. Now, going on to the power management, the LDO, like I'd mentioned before, synchronous rectification MOSFETs, right? That is going to lead to higher efficiency, lower switching and conduction losses. And then buck boost converters to provide the power rails and for all the different components in the circuit, the CPU power, the sensors, all the other auxiliary components. And then the power stage. As I had mentioned before, power stages are really important because computing is going to require so much more power. So you need to provide high voltage, low current rails to the CPU unit in order to be able to handle the bandwidth of computing that's required. And then motor and traction control. Motor control, multi-axis motor control is very, very important. It's encompassed in power modules, MOSFETs, and gate drivers. And these MOSFETs have to have very low conduction losses, right? So when we talk a little bit further in the presentation, I'm going to show you the vertical trench structure and how we create that value proposition through the design of the semiconductor. So it's very important to have reliability, too, with these types of systems, because with motor control types of designs, you have so many things that can go wrong. You can have motor stalls that can put a lot of current through the MOSFET, and so the MOSFET or power switch or power module has to be able to have that survivability. And then for wireless communication, Bluetooth low energy. It's a very low power transmission source. And then object detection with LiDAR imaging, power over Ethernet. These are some of the key systems to provide the feedback in terms of providing the robot direction and then providing safety for the coordinated movement that goes inside the plant. And then sensors. Accurate op amps are going to be needed for sensor measurement. You know, zero drift type of architectures, very low offset voltages. Those are going to be some of the key technologies or key functionalities inside measurement devices to be able to sense what's going on in the environment. And then for communications, Ethernet. So Ethernet transceivers, whether they be CAN, whether they be Ethernet, whether they be FlexRay, a lot of the communication protocols from automotive industry are starting to carry on over into Industry 4.0. Now the shielded gate trench silicon MOSFET structure. So how do we create that value proposition for low power loss and efficiency? So the technology is really geared towards lowering switching and conduction losses. So you want to optimize the switching and conduction losses so you can extend the battery life. So some of the important characteristics, you have small size and you have cheaper die cost versus a planar type of design. And you're exhibiting low capacitance for fast switching speed, for component reduction, and a low resistance that's highly robust. So right now, with the technology that's out there and the technology that's kind of been in the market, you've had to make a trade-off between resistance and capacitance. So if you lower the resistance, you're increasing the capacitance, and vice versa. But with this shielded gate trench type of structure, you're really decreasing that trade-off that you have to make. So the shielded gate trench structure optimization is really dependent on the construction of the following areas. So I'm going to point out a few. So the epi layer. The epi layer thickness and the epi layer resistivity is based off the doping that you put in this region. So the more that you dope this epitaxial layer, the lower your drift resistance is going to be. And the drift resistance is the biggest contributor to the resistance or the RDS-on that's in MOSFETs today. So I enhanced this structure by putting a shielded gate type of configuration. That shielded gate structure, which is kind of shown here, really what that does is that when you're building into the trench structure, you're able actually to then reduce the capacitance. And also what contributes to it is the depth of the trench. The depth of the trench really has an effect on how much you can dope into the epi layer. But if you make that trench region a little bit too deep, you're giving up the capacitance again. Other factors are the gate oxide thickness. And then also the width between the different cells within the structure. That has an impact, too, on the RDS-on and capacitance trade-off. So encircled here is all the different resistances that contribute to the RDS-on. So the goal in really turning those knobs is we want to lower the RDS-on as much as possible without compromising the switching performance. So a couple of graphics that I want to reference the audience to is the one at the top right. With the shielded gate structure, you get much less ringing during switching transitions versus when you have a typical trench type of structure. And then, in terms of having the best cost for the lowest RDS on, the planar devices have the highest RDS on per area, the trench being a little bit lower, and the shielded gate being the lowest. So you're getting, with the shielded gate, you're getting the best RDS on per cost because you have a much lower area of resistance or a specific resistance. So package technology enhancements, I'll go into that a little bit. And these are some of the packaging technology enhancements that we have for better performance, better lifetime, better reliability, and enabling more PCB cost savings. So this is going to help enable longer operation times, and you're going to have a much lower cost of ownership. So the first thing on the left-hand side, the power clip bonding. So the transition from the wire bond type of configuration to a power clip type of configuration is that you're able to spread heat so much better throughout the part, and you're lowering the thermal resistance of that part. So what you have with the power clip type of configuration, about a 40% reduction in RDS on versus using a wire bonded type of structure, and then a 40% lower R theta JC, junction to case thermal resistance. Now with the dual side cooling, which is in the middle graphic there, you're taking heat out of the top and the bottom side, leading to more space and cost savings. So the dual-sided cooling type of configuration allows you to have more reduction in complexity in the PCB, so you have a smaller heatsink design. You're able to reduce the vias in the PCB to be able to channel the heat much better, and then you have less layers in your PCB, while at the same time you're keeping control of that junction temperature. You raise that junction temperature, your RDS on and your resistance goes up. So to be able to control that, one of the innovations in the packaging is having this double-sided cooling. One of the packages that are kind of taking the market by storm right now is this top-sided cooling package, the ability to take heat out of the top side of the board. And you're leaving space for more components, and you're allowing more PCB board reduction by doing this. So you have space for more components on the bottom. You're able to shrink the board size. And with the gull wing packages that you see at the top right, you have better board level reliability. So if you're temperature cycling and you're connecting with a gull wing type of package, you're actually able to have much better board level reliability, less solder cracks, and just longer operation over the lifetime of the system. You're actually lowering the PCB board temperatures too by taking heat out of the top side of the part just to ensure that enhanced reliability. So motor drive systems, I mean, they're an integral part of robotics and industrial automation type of applications. So efficiency in these motor drive systems is an important consideration because of the fact that they consume more than half of the electrical energy that's consumed in the design. So the innovation that we've done in our power module packaging is this transfer molded power integrated module, okay, that's been designed to answer those robustness and reliability challenges in industrial motor control systems and servo drives. And what comprises these transfer molded modules is that they're IGBT and fast recovery diode based type of configurations. And so at the bottom of the slide there, what you can see is the different configurations. You've got the CIB, CI, and the CIP. So I'll talk a little bit about the CIB. That stands for converter, inverter, brake type of application. So with the converter, you're taking the three-phase power source and you're rectifying it. With the inverter, you're providing the energy to the three-phase windings of the motor. But then, any back EMF that's created by the motor, the brake circuit kicks in, and it prevents the capacitor from overcharging, right? So you've got reliability, and you've got integrated performance all in one package. So if you look at the graphic at the bottom right, okay, the power devices are attached to a direct bonded copper substrate, which is noted as a DBC down there. And it's connected through aluminum bond wires and to a lead frame. And the really important thing about this DBC, this direct bonded copper substrate, is that it's an aluminum oxide-based substrate, and it's really essential in limiting the thermal resistance to keep the device heat lower. That is the innovation, and that is the trend that you'll see in these power module types of designs, is the use of this direct bonded copper type of structure. So in comparison to some gel-filled platforms that you see out there in the market today, you have much better efficiency. So you have lower collector emitter voltage on the IGBT. You've got the adequate short circuit withstand time, right? Short circuit withstand time is a very important consideration for IGBT design. You have better power and temperature cycling capability, and you've got a higher lifetime and reliability, and it meets IEC safety standards. The epoxy molding compound that comprises the construction of the transfer molded platform, it's extremely advantageous for extension of the lifetime of the module. And one of the great things about this device is that a thermal interface material can be applied on the top surface of it to keep the device temperature even lower. So for even more enhanced integration, you can put a gate driver unit into the inverter. So the gate driver unit and the inverter unit, it can be combined into the same structure. Okay, so similar to the transfer molded structure, it integrates that direct bonded copper substrate, that DBC substrate material, to limit the heat dissipation and keep the thermal resistance lower for the higher reliability. And for diagnostics, going back to the intelligent power, it also integrates a shunt resistor, thermistor, ceramic capacitor, and resistors for filtering, and temperature and current measurement. So the capability inside of the device so that the power delivery can be controlled, right? And you can shut the system down if you're in any risk for damage. So it's a great example of intelligent power. Diagnostics to provide feedback to the system. So various flexible topologies can be integrated into one package. It's built with an isolated gate driver, silicon MOSFET and IGBT power switches, and then power diodes that feature fast recovery. So you get it all into one package with limited inductance, limited resistance. So going back to the question of, okay, where does silicon carbide fit into the picture of industrial automation? Industrial robots and servo drives. That's a great potential application. A good application fit, for the industrial motor drive, where the power requirements are in the high kilowatt range, and you have a voltage bus potentially greater than 400 volts DC. So the 650 volt silicon carbide device could be something of interest in these types of applications. And going on to a little bit more shameless promotion, onsemi, we provide the entire vertical supply chain from the boules to the die to the packaging. Okay, so right now we've released a planar technology that's encompassed in these planar dies, this M1, M2, and M3. So the M1 type of design, it's a square cell type of design, 200 micrometer wafer thickness. It's got a very large die size. So it's got a very, very low thermal resistance, and it provides a good balance between switching and conduction losses. So you have a good, balance, to be able to have, use in wide range of applications. Now, moving on to this M2 type of die, it's an hexagonal cell type of design, and it features a 100 micrometer wafer thickness. And so this results in much better RDS(on) per area, better reliability, and lower thermal resistance, and it's very, very good for lower speed type of applications. The M3 is kind of a pseudo trench type of design. It's a split sill FET that creates very competitive specific resistance in that M3 family. And that die is actually optimized based on the need for any fast switching and lower RDS(on) with the capability for higher gate drive. And so just talking a little bit about the turn-on loss of a 3-lead versus a 4-lead device. So with the 4-lead device, you have that Kelvin sense pin. That's one element that we're adding to create the efficiency for Industry 4.0 and also automotive applications. That Kelvin sense pin allows you to reduce your turn-on loss by about 74% when you compare a 3-lead and a 4-lead. Now, when you compare the same 3-lead to the TO leadless package that we just released, the TO leadless package also has the Kelvin source pin. So you're able to have much lower EMI, much better switching, and also a reduction about 68% in the turn-on loss. So talking a little bit about connectivity. So connectivity, it's essential for asset tracking. Oh, okay. Yeah, so just really quickly going into visible light communication, angle of arrival and angle of departure. These are 3 things that you can do with the RSL15 and the visible light communication. And then a closer look at our image sensor. It shows the evolution of the design, this wafer stacking approach for better performance yield and smaller imager design footprints. And then some of the key takeaways. I'll let you guys read those, but yeah, we have the technology to realize intelligent sensing and power. So with that, thank you guys for your time.